Hey, what's up everybody? We're back for some more VSEPR Theory fun. This time we're going to look at describing the shape of a water molecule, H2O. Again, the first thing you want to do when working with geometries is draw out the Lewis structure. So let's do that first. Step 1. Determine the total number of valence electrons in the molecule contributed from each element. Hydrogen, it's got 1 valence electron. Oxygen, 6 valence electrons. Boom. Keep in mind we've got 2 atoms of hydrogen, each contributing 1 valence electron, for a total of 2 valence electrons contributed for this molecule. Oxygen, on the other hand, we've only got 1 atom of oxygen, but each atom has 6 valence electrons, so 6 contributed from our oxygen. Total, we add them together, 8 total valence electrons contributed from all of my atoms in this molecule. Step 2. Determine the total number of valence electron pairs available. So we take our total number of valence electrons determined from step 1, divide by 2 to get our total number of valence electron pairs. Step 3. Build our skeletal structure by choosing a central atom. Again, you're going to go to your periodic table, remember your trend in electronegativity, but in this example, again, I've got hydrogen as one of my elements, and that one is never going central. So oxygen's going to go in the middle. I'm going to surround it by my other atoms, in this case, just 2 hydrogens. Step 4, place a pair of electrons between that central atom and each of the terminal atoms. Again, I'm going to color code here to help you recognize that one of the electrons in that pair is coming from the central atom and the other electron is coming from that terminal hydrogen. This time, I only need to use 2 pairs to connect my central atom to the terminal atoms. I have 2 pairs left over. Oh my goodness, what am I going to do? Well, turns out if you have pairs left over, the first thing you do is you try to give them to those terminal atoms. In this case, my terminal atoms are hydrogen, and they're not going to accept any additional electrons. So if you can't give them to the terminal atoms, you give them to the central atom. Oxygen is more than happy to accept them. I subtract those 2 that I used to give oxygen its octet. I have 0 pairs left over. I want to stop and check and make sure that every atom that needs an octet gets one. In this case, oxygen is the only one that needs an octet. My hydrogens are completely content having just 2 electrons. That completes their valence level. Again, don't forget you can represent the Lewis structure with those bonded pairs of electrons represented by dashes. Alright, so we have drawn out our Lewis structure for a molecule of water. As I look at that structure, it appears that the regions of electron density around my central oxygen atom are all about 90 degrees from one another. However, let's think about what this is going to look like in 3 dimensions. This time, my central purple atom is going to represent an atom of oxygen. I'm going to add to that 2 singly bonded hydrogen atoms, and I'm also going to add a couple of lone pairs. So I'm going to take a minute and just sort of swing my molecule of water around so you can get a chance to look at and examine the geometries and hopefully recognize that they are not at 90 degrees from one another. Taking advantage of that 3-dimensional world that we live in so that those electron pairs can get as far away from one another as possible. Now, we've got 2 geometries to describe here. The first is our electron geometry, or what shape do my electrons take? And again, it's easiest to do that simply by counting up the total number of electron regions around your central atom. In this case, I have 4 regions of electron density, and therefore my electron geometry is tetrahedral. However, the shape of my molecule, or just the bonded atoms, is bent. And the reason why it's bent is because we have those lone pairs of electrons on the central atom as well. Now, when it comes to bond angles, if I were to have 4 regions of electron density and all of those regions ended in a bonded atom, the bond angles would be 109.5 degrees. However, note that the bond angle between my atoms here is actually a little less than 109.5. And that's because those lone pairs of electrons repel a little more strongly than those bonded pairs do.